Good afternoon, everyone. My name is Songwei Zhou. I'm a research scientist at Johns Hopkins University. Today, I'm very happy to present our recent work. Actually, it's not recent anymore. We have been spend a lot of time on this project, and this project is still ongoing. It's called Body Maps. The goal of this project is to build a 3D atlas of human body for each individual. And this project has been funded by Lars Garden Foundation. I'd like to start with Google Map because the goal and concept is very similar to body maps. Google Map tried to transfer the raw data, which is a satellite image on the top left, into the information that everybody can understand, and then extract the useful knowledge from this information and eventually lead to multiple everyday applications, such as Lyft and Uber, and so on. The observation is the raw data is not really directly useful because it's a bunch of pixels. And the information try to make sense what is in the image, such as buildings, street, road, everything. And the knowledge help us make decision and actions based on the information. And finally, the application is what we really use every day and to make real-world impact. In medical domain, it's the same thing. I take the CT image as an example. It's a grayscale image modality, not directly understandable to most people. Maybe only medical professional can understand them. So we try to transfer this raw data into the information so that even patient or other student can understand it. So to do this, it's simply ask people to annotate the pixel in the CT image to tell it what is what. For example, organs, vessels, muscles, bones, or even disease in the image. And then based on this information, we can make a clinical decision or measurement, how big it is, and a treatment based on this anatomy. Finally, if this can be done, a lot of clinically relevant application can be made. So here I give the example of a virtual reality to help the not only doctor, but also patient communication and medical education. And even everybody can get access to this tool. Or even robot. So now the computer and the robot can do many things more precise than human do. Google make a map for the Earth, and we would like to map the human body. For us, especially CS people, we would like to let AI understand the internal structure of human body, essentially to let it understand everything. So it's conceptually easier than natural image because in the real world, there are so many different classes, but in the human body, the number of organs, bones, and structures are a lot, but they are fixed. So it's a manageable amount of effort. A little bit background about the raw data we're using. We use CT, computed tomography. And this is different from the normal camera because it can take a picture of your internal structure and do the image reconstruction. So eventually the CT scan will be the 3D picture of your body. So this make it possible for us, for computer, to understand what is happening in each individual patient. Now, the most expensive part is to transfer the raw data into useful information. So this process we call annotation, which requires per voxel annotation to extract the information from this data to assign the semantic class label to each pixel. So this task for natural image, it might be manageable for everyone, so you can ask many people to help you do that. But for medical image, not many people can do this task. It requires some medical expertise. And also medical image, as said, it's often in 3D. It's more time consuming and tedious to annotate these pixels. Again, the number of classes in human body is manageable compared with the natural images, but it's still a lot. So building the body map will take a lot of time, and it have motivated us for several years. Recently, we present body map 1.0 version. We call it abdominal atlas. So we first start with the abdominal region because there are so many different important organs in this area, and it presents very complex anatomical structure. Many diseases are associated with this area, and it's extremely important for early detection of cancer. So we try to make the 3D map of human and abdominal region. In computer vision term, we make the semantic segmentation mask for each important pixel for the organs, bones, vessel. And as you can see, the resulting image is very similar to a map of human. Each component is like island. It's like island in the Google map. Since the body map is very much motivated, you may wonder why it's so hard to create one, or why it's hard to create for everyone. We perform a simple reader study. We ask the radiologist to sit down and actually annotate these pixels. We estimate to annotate one organ in one CT image. It requires a radiologist for on average 30 minutes to complete. And this annotation time will significantly increase if the organ are large, such as a colon, intestine, and if the organ are with unclear boundary, like pancreas. In addition, some CT scans are low quality, themselves are very blurry, so it's very hard to distinguish the boundary of the organ, even by human eyes. So these factors all increase the annotation time. Again, this annotation process must be done by medical professionals who are very busy and expensive. We made an estimation to finish fully annotate 8,000 patients. It will take one radiologist over 30 years to complete. So up till now, it seemed not very convincing that they must spend so many efforts to help AI understand human anatomy. Then how do we start this project? How to reduce the annotation time? A naive structure is to randomly select the CT images and ask radiologists to annotate everywhere. So this really take time. But we propose so-called active learning method. The result are very promising and exciting because we managed to reduce the manual annotation from 30 years to 3 weeks to complete the annotation for 8,000 CT scan. How we do that? We don't ask people to randomly annotate image anymore. Instead, we use active annotation. We first pre-train an AI model and inference it on huge amount of unlabeled data. And then we develop some criteria to select the most important CT images. And within this image, we select the most important regions. And we send this to the radiologist to manually revise and edit. Then this data will be saved to the labeled image. And use this newly labeled image, we fine-tune the AI model to improve the performance and inference it again, and select the most important image again and the most important region again for human to annotate. So you can see here the loop, and this loop try to focus on the important information that can improve AI performance the most. The difficult part is how to select the important CT image and how to identify the important region. We use two criteria. One is entropy-based, another one is diversity-based. The intuition of entropy-based method is to draw radiologists' attention to the region that confuse the AI algorithm the most. To how to find this region. So we use a so-called attention map. So here the red area is the important region we want radiologists to pay attention and edit. And other regions, we assume the AI prediction are accurate enough. To create this attention, we select the inconsistent prediction from multiple AI model. And we select the area that AI prediction is with low confidence. And also we select the region that AI think one pixel correspond to the two or more different class, which is will not happen because the one pixel can only correspond to one class. Another project called diversity. The intuition is we do not want the human annotator to correct the similar error made by AI again and again, because we found a typical error, AI can learn from a few corrected example and never make this mistake anymore. So for example, the stomach, usually AI will predict the uh, air region in the stomach as not belong to stomach. But after radiologists correct a few sample, usually two or three, the AI can fine-tune on these samples. It can already learn and make a very good predictions. So we summarize the taxonomy of common error made by AI so that we can select the most diverse type of error every time. So with this active learning approaches, we really make this happen to annotate the organ and the other structure in a large amount of data. And so far, we have released over 9,000 annotated CT volumes and 231,000 organ masks. So this is abdominal atlas, and it's already public available online, and you can download for your research. And it was also included in the MedShapeNet. So apart from what has been released, there is an even larger internal annotated dataset at Hopkins. So we collect as many as public available CT images as possible. And we annotate a lot of organs and other structures based on the active learning and human in the loop. And we collaborate with teams of over 10 radiologists. We are working on releasing them to the public as well in the future, but this data set is ready and can be used for internal collaboration. And this data set is big and also it's diverse. It comes from the multi-center. This is important for medical AI because usually medical data set is small and is biased to specific center. There are many public available data sets that come from only from one or few hospitals. And our data set come from 94 different hospitals from 19 different countries. This is important because the AI trained on the diverse data set. Its robustness robustness will be improved. And I will comment on this later with some experimental result. And our data set also diverse in terms of a patient demographic, such as gender, age, and scanners. The second feature is we have annotated multiple structures. Currently, it's not as many as the total segmentator who have over 100 different structures annotated. But here we annotate 73 structure. Most of them are abdominal organs. And we also include the lung and vascular system, skeleton system. So this is a screenshot of publicly available dataset. Each row is the name of the dataset, and the column is the name of the anatomical structure. The green dot means in this dataset, these class are annotated. And in gray dot, it means this is unannotated. So you can see the public available dataset as a combination. They provide a lot of CT images. But if you want to use them all, you will find the resulting dataset are partially labeled. So our contribution is not really to create new CT images. We took the current CT in the public dataset and use human-in-the-loop active learning to annotate or to fill in all the annotation in these missing classes. And also we added 48 additional structures. So it resulted in our abdominal atlas. All the CT scans are public available, so you are free to use. We don't have any ownership of these CT images. What we contribute is the SIME, or it's the annotation, per voxel annotation of all these 73 structures. And the third feature I want to highlight is our dataset, the annotation quality is pretty high compared with the existing dataset. So nowadays, the AI pseudo label can be very precise. So there are several datasets, their annotation are completely created by AI. So this will lead to some inaccurate for some hard structure. For example, stomach, as I commented before, usually AI prediction are incorrect because of the ear region. And we have a human to manually annotate them and retrain the AI to make it perfect. And also other bigger organs, the annotation quality can be bad because of the the tedious process and the low quality of the CT image. So we make some comparison between the label quality of our dataset and the existing public available dataset. So this really take effort and time to make the high quality annotation, especially for some challenging organs such as colon that I make an example. Colon is, to be honest, the colon is very, very difficult to annotate and extremely time consuming. The boundary is not clear for most scan. In order to make the quality higher, annotation quality higher, when we talk with radiologists, we somehow made an annotation standard for each class, especially for the challenging class. So here the colon, we make agreement that colon is a continuous structure. So after the radiologist revise the colon, when they visualize the 3D rendering, this should not be incontinuous. Same concept as the intestine. So we make this annotation standard clear, not only help the annotator to revise and edit the AI prediction, but also make it easier for the senior radiologists to double check their revised annotation. Another challenging part is vertebral and bone segmentation. So this structure, it's easy to segment because the intensity value are different. It's very bright in the CT. So we essentially do not need the AI to do the segmentation necessary. We can use some automatic way to like thresholding to make a pretty good annotation. But based on our observation, this is not enough. So human manual annotation can still do a better job, significantly better job. Here is the example of annotated ribs and vertebral in total segmentator. From a quick look, you can see, oh, it's pretty good, but really take a closer look, you can see the number, the index of the vertebra are usually misplaced, and the ribs, especially the end of the ribs, are incomplete. So this require manual editing, and we do this. So here the annotation quality will be better, significantly better than all, we can see all the existing public available data set. Since we build a large-scale annotated data set, we are thinking to create a large-scale benchmark as well because we assume many people will be interested in this. And there are so many advancements in semantic segmentation area in medical image field. So we make an initiative to invite almost all the AI algorithm inventor to join us to use our data set, train their backbone, their own backbone, and we provide an internal data set at Hopkins for the out of distribution evaluation. This benchmark, we call it touchstone benchmark. It is very unique because you almost never see a public challenge that invites so many first author or last author of the AI algorithm to join this competition. And most of them nowadays, it's already a professor. So we really appreciate their effort to join our benchmark. And we have a 53 group confirmed the contribution, and we already have a preliminary result in ISP and MICCAI this year. The first edition of our benchmark has been accepted to Europe this year, and it is a MICCAI challenge, and the result will be presented in a few days in MICCAI. You can see a lot of familiar name in our author list because you might already somehow use their architecture for your own research as a baseline. So here in this benchmark, we do not train any of the architecture ourselves because we do not want to inject any bias into it, or we do not want to tune their hyperparameter. So we keep it fair in the sense all the creator of the AI algorithm themselves train the model on our dataset. And what we do is to take their checkpoint and do the out of distribution test on our private JHU dataset. So on the right is the result of the first edition. And this benchmark is still open, so you are very welcome to join it anytime. Send us the checkpoint, download the data, and we will do the evaluation for you. This benchmark is the big collaborative project and involve a lot of famous institutes around the world. Again, all the competitors are the first or last author of the famous medical architecture backbone. With the large annotated data set, another thing we are doing is to build a foundation model for the medical imaging. I realize that different people have a different definition of foundation model because it's somehow a cool name recently. And in my talk, this refers to the AI models pre-trained on a large-scale dataset. No matter it's annotated or unannotated. And this AI model can be adapted or applied to across different tasks. So in my old day, we usually call it a pre-trained model, but now I will also in our paper we also call it a supervised pre-trained model. In short, Supreme. When it comes to model pre-training or representation learning, there are usually two options. One is called self-supervised pre-training. Another one is supervised pre-training. Self-supervised pre-training do not need any manual annotation from the human, and the model can train from the raw data. For example, you mess up the raw data and ask the AI to reconstruct the original data. That's what I did in 2019. And another famous way is to contrast the learning, to ask a model to learn from different images. Self-supervised learning has been popular, and the number of paper and study increased rapidly. But in computer vision, there are another option, which called supervised pre-training. And this usually done in the ImageNet dataset because it is an annotated dataset. But there's, at least currently, by now, there's no medical ImageNet public available that can allow us to do this supervised pre-training. And our abdomen atlas, it's somehow big, but certainly not big enough. But we provide more detailed annotation compared with ImageNet. ImageNet is a per image annotation, and here we provide per voxel annotation. So in this sense, the number of annotation unit is comparable to ImageNet scale. We are doing a study to compare whether in the medical domain, whether the supervised pre-training is more powerful or self-supervised pre-training. We have some interesting funding in terms of transfer learning ability because by definition, AI model pre-trained on broad data, you will assume supervised pre-training will require a very, very expensive data set. But according to our study, it's not. So here is a plot. The axis is the data, number of data for pre-training, and Y is the transfer learning performance or ability. And the red dot is the supervised pre-training, and the gray is the self-supervised. It's a state-of-the-art self-supervised pre-training. We found if you use the human annotated if you use the human annotated images, the model only have to train 20 CT scan. The transferability can be similar to model trained on 5,000 unlabeled CT scan. And the supervised pre-training is scalable because if you add more annotated CT scan, the transferability can significantly improve. So this come to the balance. You said the human annotation is expensive, but GPU hour is also expensive. And train on so many CT images, those unlabeled CT images are time consuming. If you can ask people to annotate 20 CT scan, which might not take too much time, and only use 40 GPU hours, the AI transfer learning capability is similar to this 5,000 CT. This is a very interesting result. Suggests that supervised pre-training has a big potential in multiple downstream tasks, and it's not as expensive as we thought. And we demonstrate this on one target task about pancreatic tumor detection and classification. And there's a project called Felix project. We are already pushed the AI performance better than similar or even better than human performance. Its sensitivity specificity pretty high. And using the AI supervised pre-train on the multiple organs dataset, abdomen atlas, the performance can even get better in tumor detection task. And here is another independent research about the power of pre-training. So they basically took our pre-trained model, adapted to the lesion segmentation task, and also find the improved performance. Lastly, I'd like to comment a little bit about the clinical application about the body map. Suppose we can finish the body map. So currently we have a map the human and abdominal region, and eventually we would like to build the three-dimensional atlas of the entire human body. The first application would be the medical education and the patient communication. So you no longer have to show the medical student the template, the perfect exemplar patient body like this, and instead you can show them a lot of patient in the clinical practice. So there is a very similar product on this. It's also based on the the organ segmentation, and it have implemented into the VR system. The issue is this product are the AI was use the total segmented dataset, and it is only 1,000 images, and some of the most of the label quality are good, but some structure the quality still require human revision. And this is our own demo of the VR. We also have a collaboration with the VR team at Hopkins. And we implement not as fancy as the conventional commercial product, but still our algorithm and annotation is much accurate than the AI direct inference pseudo label. And we try to implement this with the human in the loop to make the annotation faster and make the visualization more faithful. We showcase this in the JHU CS Alumina Week and implement into the VR glass and ask people to play with it, to zoom in, zoom out the body, and check the internal tumor in the liver and so on. And we think this personalized atlas of a patient can really improve the healthcare output and potentially useful for the robotic surgery as well. So currently, it's still a prototype, and we are very welcome for the potential collaboration with you. There is JHU news about our project, AI and the radiologist unite to map the abdomen. The takeaway is that while a dataset of this size would have taken an experienced human annotator almost 31 years to fully annotate, and the team completed this task in only 3 weeks. I'd like to end my talk with a huge thank to my advisors and all the collaborators. Thank you very much.